Can you also do cross product from as well?
Yeah, because it's a sign.
Okay, and then this should be 0, right? So that's what we're trying to show. And then, what, and somebody else said cross product?
Would just be the product of their magnitude.
Would be the product of their magnitudes, wouldn't it? Because a cross product, remember, magnitude of that is the product of the magnitudes of each vector times the sine of the angle between them. Okay? So if we could show, if we showed that, we'd have it, or if we showed this, we'd have it. Okay. Let's go ahead and come back and grab this. Just look at that. So what we're going to do then is we're going to take the I terms and multiply them together. Okay? And then we're going to multiply the j terms together. We're going to add those. Okay. So multiplying the I terms, notice there's a common R omega. And we're multiplying two I terms that have R omega in common. So it's going to be R squared omega squared. And one of those terms had a 1 minus cosine theta, and the other one had a 1 plus cosine theta. Which we know, and then let's go ahead and get the rest of it on there, and we're adding on to it then the product of the j terms, which happens to be minus R squared omega squared sine squared theta. So there's our dot product calculation. And we end up with this, and this is a difference of squares. And this is sine squared theta, right? So zeroes out. So this all zeroes out, illustrating that they're perpendicular. Could you look at these two vectors and the fact that your triangles are isosceles in both cases and do the geometry instead of relying on the dot product like we just did? This is some angle phi. Here's some angle gamma, 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 and phi, phi. And what should be true about the relationship between phi and gamma for these vectors to be perpendicular? What if you laid one sketch on top of the other? Phi and gamma's relationship should be, they should add up to 90 degrees. So phi and gamma there, phi and gamma should add up to 90 degrees. Okay, so another approach here then, instead of doing the dot product, would be that phi plus gamma should equal 90 degrees. And you can work that up from the isosceles character of the triangles here. And the fact that theta is in common in the relationship there. So theta, look at this geometry. What's theta equal to in terms of gamma over here? 2 gamma. 2 gamma is theta on this picture. That's a basic thing that's useful to remember from geometry. On an isosceles triangle, those two angles are equal to that angle right over there. Okay? So that'd be pretty easy to show. I'm not going to take the time to do it. Okay, very powerful, the vector approach, but don't forget how powerful this little bit of graphics is. Try to do the graphics also while you're doing your vector solutions. Any questions at all about that? Okay. Let's stick with this topic for a minute, and let's go over let's investigate a problem like number 74. Once again, they split the discussion here from the picture. So here we have I'm sorry. Get this so we can read it. There we go. Pin of the rotating arm OA engages a slotted link and causes it to rotate. Show that the angular velocity CB is 1/2 that of OA regardless of angle theta. So the picture associated with this is this one right up here. And there is I guess you could call it a trick associated with these types of problems, and it's probably worth taking a few minutes to look at it. We have a mechanism that is at some angle theta to the horizontal here. And then we have another arm here. Then we have a pin hooked on there. And this is a guide. Member CB, and the pin is hooked down to a rod that connects over here to point O, I believe. And then that pin is P. And these distances, this is some fixed length B, and here's B, here's theta right here. And this is point O. Okay. So using that geometry piece of information that we had from earlier is if this is theta, this is B, and that's B, then that means that this triangle, this oblique triangle, remains isosceles. And so this angle over here, which relates to the motion of OP, is what? Twice theta. So theta sits up here, and theta sits over here, so that again is twice theta. Now, they gave us what piece of information in the description of the problem?
They only give us the RNA, so maybe that's 0.
This member, which extends on out like this, which they call OA, that has pin P on it. Okay, they give us that omega. So they give us that omega of OA. That was given. And they want us to show that, what's the relationship we're trying to show?
That the omega of
B.
CB is 1/2 that of OA regardless of angle.
Okay, so we want to show that omega, and I usually put things most of the time in alphabetical order. I didn't do OA in alphabetical order, but I will do BC in alphabetical order. We want to show that omega of BC is 1/2 of the omega of OA. Is that correct?
Regardless of the
Yeah. Okay. For any theta. So we're trying to show that this relationship's true for any theta. Okay. And we're trying to do this using relative velocity. And this relationship always remains true. Theta here, theta there, 2 theta always here. Let's see if that works. That's not what they used. That's not the approach they used, but let's see if what you just suggested works. So, right here, we know that the time rate of change of twice theta with respect to theta is equal to the omega of our member OA, right? Here's our defining angle of giving us the orientation of OA, and the time derivative of this is 2 theta dot equals omega OA.
Divide by 2, and there you have it.
but theta dot relates to the motion of the other arm over there, doesn't it? And this is the omega, is the time rate of change of this omega over here, or this theta over here, time rate of change of this. And so this is then going to be your theta dot is then going to be your omega of BC. Done. Okay. Now, I'd like to go a little further with this. That was very nice, very simple, nice, straightforward approach. Any questions before I go further with this? Okay. When we have, what we're going to find we have to do in more complex problems, and this is starting to get into that realm, is when we have something that's moving on another rigid body. There's a couple of ways of handling this. One really common way to do it is momentarily imagine that there's another point that's instantaneously coincident with point P. It's sitting right there where P is, but it's part of the other member and stays part of the other member. So what I'm going to do is I'm going to put another point on there, and we'll call it P prime. So we're going to put another point right there, and we're going to call it P prime. Now, P prime is going to be moving in a circular arc. It's hooked on this member BC. P prime is on BC. And that's moving, that point, that fixed point on there, coincident with P, momentarily, is staying on a radial arm from C, around C. What's the motion of point P, though? As you allow 2 theta to increase some, what's the motion of point P? Circular path about this point. Okay? So what you want to do with those kind of situations is you want to draw those apparent paths. So this is the path of P, and the orange path is the path of P prime. Does that feel okay? Now watch what happens if we allow theta and twice theta to increase a little bit. If theta increases a little bit, then that means we're now up in here, aren't we? And P is now where my thumb is, and P prime is where my index finger is. So what's the apparent motion of P prime relative to P? It's along this direction, isn't it? At an instant. So P is moving out that way, away from P prime. Imagine a little bit of rotation to occur. The pin here has to stay in this track, and as that pin gets driven counterclockwise to the left, this arm is rising up that's got the P prime on it. And between my index finger and thumb is the relative separation between the two that occurs. And that is in that direction. So the velocity of P well, let's see, which way do I want to write it? Yeah, the way I was saying it, the velocity of p prime relative to p is outward along CBC.
I'm sorry, Robert, but you lost me P prime.
Oh, finally lost somebody. It's been 8+ weeks now. I finally lost somebody. Okay. Okay.
Glad I
Good. Okay. So let's go back to what we do is we define when we have something moving, we usually define its position. In this case, we define point P. Point P is a pin. Sits inside, and it's rigid on this, it's hooked to this OA arm. Okay, so it's like a ball hooked on there. And that ball is required to rotate like this. Okay? That should be all right. Now, what we do is we put another, if we have another rigid body hooked to that, where there's relative motion allowed between those two, then what we do is we take a momentary, at an instant, in the geometry shown, we put another point that happens to be right there where P is, and we call it something else, P prime. P prime is a point that's etched on the other member. Its motion then has to follow, that point P prime has to follow that orange arc. And as you let the mechanism move, the point P is going to be driven back down that slot while P prime is staying there at that point on the slot. So P prime is moving out away from P. I can't get my arms moving nicely that direction, but we could, can you visualize it? I don't have the nice visual aids that we could do in a lab where we could actually set that up, but you can easily see it if you build it. And so there's a relative velocity then of P prime that is going to be, here's your BC arm. And so the relative velocity is that direction. It's outward that way. If you allow a slight increase in these angles to occur. The reason that's useful is for mainly when you're going to be doing acceleration problems. And you might see it in a little bit of the homework here. And so what I think would be a good idea is for us to let's write up a velocity equation here and see what that might show us. So the velocity, and I'll grab my notes that I was fiddling with earlier today. I wanted to write, and my work didn't quite come out the way I'd hoped it would. If I write the velocity of P prime is equal to then the velocity of P plus the velocity of P prime relative to P. We should be able to do that, right? I mean, that's a... Okay. P and P prime. You know something? I don't even think I'm going to do this because I think I know why my work didn't come out right earlier. But mathematically, this would be okay as long as we played with it properly. So I don't even want to, let's not waste our time on it right now. I just want to make you aware that we want to have this knowledge of putting a coincident point like that on there. Okay, let's not do that. Okay. Let's go over and see if I can find another one. I think what I want to do is take this problem, which is number 89. It's the latching device where rotation of link OBA, this link right here, is controlled by the rotation of the slotted link D about point C. If member D has a clockwise angular velocity of 1.5 radians per second when the slot is parallel to OC, determine the corresponding angular velocity of AOB. Solve graphically or geometrically. So we have 80 millimeter links on that, horizontal and vertical.